that are going to be attending the 2022 AOGS meeting in Honolulu can expect, in addition to a really outstanding program, lots of other cultural things that we have planned. For instance, what we had planned and what we did in 2018 was a tour of the Pacific Tsunami Warning Center, tour of the Hawaii Institute of Marine Biology facility, part of the school that I work with, the School of Ocean and Earth Science and Technology. Have a group of coastal geologists who led a field trip around the south coast of Oahu. There were a couple different walking tours around Waikiki, one that had a sail extension, meaning going out on a sailboat. The things that unfortunately we were not able to do last time were field trips to the Big Island to see Hawaii Volcanoes National Park. Of course, 2018 was when we had the last big eruption of Kilauea. So those field trips unfortunately had to be canceled. But next year in 2022, there should be lots of really interesting parts of the Big Island to see where the 2018 eruption happened. Other possibilities also will be to visit southeast Oahu to look at the geology of that area, including the Hanauma Bay area. And of course, lots of free beach time after the sessions are over. Well, as you know, in the past year, tourism was basically shut down in Hawaii. We had hardly any visitors from off the island. Of course, the economic impact to our state was not very good. On the other hand, the natural environment was really happy to not have so many people crowding the beaches and swimming in the offshore areas. So the biggest impact of this 1 year of no tourism has been the shall we say, renewal of marine life. Areas that are now reopened, like the popular area of Hanauma Bay and areas of the North Shore. Also, people are reporting that there are so many more fish than there used to be. In addition, Hanauma Bay has now instituted a reservation system. This is going to control the number of visitors, and marine life is expected to continue to thrive. Many of the parks and hiking trails, because they were shut down over the last year, the city and county took the advantage of that to upgrade the trails, make the parks a little bit more beautiful than they already were. So there were some nice advantages to not having so many people around last year. Honolulu is really a great city for having the AOGS meeting, as we found in 2018. We have a great convention center. That convention center is close to the hotels, just a short walk from the beach, lots of good restaurants around. Personally, the things that I like most about living in Honolulu is access to the ocean. In the evenings, on the weekends, my friends and I have been paddling our one-man canoes, usually at least 3 times a week, sometimes more. I've also recently been doing some scuba diving and hope to be doing some more of that. And of course, weather is a big attraction. June is probably one of the best months of the year. Not very much rain, not too hot. So we think that the venue, again, should be perfect for our convention attendees.
Good afternoon, ladies and gentlemen, and welcome to AOGS Live in Singapore. My name is El Quang, and I'm your MC today, and we are beaming live from...
Not my phone. I'll slow down to see every little thing. I'll make tomorrow a brighter place. I'll stop to smell the flowers. I won't just do it for the gram. I'll say yes to everything. This time, it will be different.
Well, ladies and gentlemen, welcome to AOGS Live in Singapore. If you heard my voice earlier, it's because I'm so excited because we are beaming live from Marina Bay Sands Hybrid Broadcast Studio. So now, this to our in-audience, in-person participants, thank you so much for coming to support us. Your presence give me the right energy, and I'm all buzzed up again. Now, obviously, we are also welcoming our virtual participants dialing in from different parts of the world. And if you are not from Singapore, I just want to tell you that we miss you in Singapore. So do come back to our lovely garden city as soon as our borders are open. Now, you may know that today's session, our conversation is based around the 6th assessment report of the UN Intergovernmental Panel on Climate Change, as well as UN Sustainable Development Goals. Now, before I hand the screen to the man of the moon, I think you know him very well, Sato-san. He is our lead organizer as well as our Assistant Secretary General. I want to tell you one fun fact about Sato-san. We share the same interest, love for running. Now, obviously, compared to him, I can't compare myself to him because he's a man of wonder. But did you know that since the 2nd of January this year, he has already run 650 kilometers. Wow, 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 wow. Isn't that inspiring? Talk about patience, endurance, and this man is like a busy man. He's, giving so much to what we do here for geosciences. So, ladies and gentlemen, without further ado, please put our hands together and welcome Sato-san on screen for his welcome speech.
Hello, everyone. Either in person participating or virtually participating. I'm really, really excited have such a wonderful event, AOGS Live in Singapore. So I'm Takehiko Sato, the lead organizer of this entire event. Today and tomorrow, we have a total of 3 very interesting panelist discussion sessions. Today's session is the first one about climate change, especially focusing on, as MC mentioned, UN IPCC AR6 report. So, of course, it's not only myself organizing the session. We have a team, co-organizers, including Benoit Thiessen and also Robin Robertson, and of course AOGS Secretariat and all other staff members, helpful, powerful team members helped to realize this wonderful event. So I'm sure you will enjoy that, and I will also be enjoying as one of participants. Okay, so before entering the event, we have a message from our society's president, Professor Chunchi Wu. Unfortunately, Professor Wu cannot make it today, but we have his video message. So after showing Professor Wu's video message, I hand my microphone back to Elle to start the session. Okay, so let's hear the message from our president.
Hello, everybody. On behalf of AOGS, it is my great pleasure to welcome all of you to attend our first ever AOGS Live in Singapore hybrid event. First of all, let me thank Takehiko, Manuel, and Robin for organizing this special AOGS event. The focus of this event is to discuss current issues such as climate change, science exploration, and geoscience education. This event is an essential activity for AOGS to engage with the community for facilitating debate, information sharing, and providing networking opportunities. Again, appreciate your support of AOGS and wish you have a fruitful time in this special program, AOGS Live in Singapore. Thank you.
Thank you, Dr. Wu and Sato-san, for your wonderful words. Now, the impacts of global change or climate change is very important to me. So much so that I'm going to bring on a special friend online. He's going to do something special for us. Now, his name is Christo Alexander. He's the General Manager of Song Division Asia. Not only he's brilliant, he's one of my, not just mine, but, Virgin Sir Richard Branson loves Christo. So Christo is going to listen into the panel, listening to all the Q&A, pick up some of the keywords, and create a unique original song and music video for our session. And it will be played live tomorrow. So Christo, how are we going?
Hello, Elle. Good to see you again, my friend.
Good to have you with us. I know that you're so busy, so we really appreciate your time. Can you tell us a little bit what you'll be looking for and what sound bites are you listening to create that song?
Okay, so I'm just firstly, thank you so much for having me. It's so exciting to be a part of this amazing event. Look, climate change is something that affects us all, and talking about it is the first step to fixing these issues. So I'll be looking for keywords and key concepts that I can incorporate into this song to bring the message to the front of the song and make sure that I express that perfectly for you. I know it's a very, very exciting time to be here, so I'm looking forward to doing that.
Can you tell us a little bit about when you hear the keywords climate change, what sort of genre or even like musical arrangement that you can think of already?
Look, I'm feeling like I need to add some emotion into this. To get us all emotionally invested in these key in these issues. So it'll be an emotive song, maybe a little bit of a fist pumper, like just getting you to feel these words and feel the emotion. So it'll be that kind of song, I think.
Oh, we are so excited. Thank you so much once again for your time. I know that you're going to stay on to listen to all what we are talking about today, and we appreciate your passion for climate change.
Thank you for having me.
Right. Thank you. See you in a while's time. Now, ladies and gentlemen, don't forget to dial in tomorrow because you'll see and hear the music video that we've created just for you. Now, this is a time where we are entering into the panel session. Now, our wonderful panel of experts will take, each of them will take about 8 minutes to present their topic. And then from there, this is a great time for our virtual participants to key in questions within the Q&A box on your platform. Now, for our in-person audience as well, please feel free to raise your hands during the Q&A session, and one of our team members will bring the microphone to you. Just a gentle reminder to keep our masks on, even when you are speaking on the microphone, okay? So our climate change panel is moderated by Dr. Lauren Shadow, and she is the Earth Science Specialist at the Earth Observatory of Singapore, Nanyang Technological University. Now, obviously, she's very knowledgeable, but what I know of her is she is such a foodie. You know, in Singapore, we're all about food, right? So she told me that her favorite Singapore dish is chai tau gui, which is a savory stir-fry radish cubes that I absolutely love. But I also know that she can really take spice, that she goes to the mala spectrum of that food. So I know you're missing Singapore. So do come back. We have lots of food waiting for you. But without further ado, please join me in welcoming Lorianne and her panel experts on stage and on screen.
Good afternoon, everybody, and welcome to this session about the UN IPCC AR6 reports. So today, we will hear and discuss about the sixth assessment report by the Intergovernmental Panel on Climate Change, or in short, IPCC AR6, which was led by Working Group 1 and which represents the physical science basis of climate change. This report was published back in August this year and involved hundreds of authors. And today I'm very fortunate and very happy to welcome a few of these authors on stage and online to discuss about these issues, as well as some distinguished climate scientists that will be joining me as well on stage and online. So the first professor I'd like to welcome is Professor Peter Thorne. Professor Peter Thorne is professor in physical geography at Maynooth University, and he was a lead author of chapter 2 of the report, which is called Changing States of the Climate System. So Professor Peter Thorne is joining us online. Next, we have Dr. Krishnan Raghavan. Dr. Raghavan is a scientist and executive director of the Center for Climate Change Research at the Indian Institute of Tropical Meteorology. He was a lead author on chapter 8 of the report, which is called Water Cycle Changes. Next, we have Dr. Tie Yong Ko. Dr. Tie Yong Ko is associate professor at Singapore University of Social Sciences. He's an atmospheric dynamicist and expert reviewer of the IPCC AR5 report. So the previous one, and Dr. Ko is going to join me in person today. Next, we have Professor Martin Wisbeck. Professor Martin Wisbeck is head of research of the unit Physical Oceanography at Geomar Helmholtz Center for Ocean Research in Kiel. He's a professor at Kiel University in Germany. His research interests involve the ocean's role in the climate system, ocean circulation, upwelling systems, integrating global ocean observation, digital twins of the ocean, and the ocean dimension of sustainable development. Next, we have Professor Francisco Doblas Reyes. Professor Doblas Reyes works on the development of global climate forecast systems and their use in climate services. He served in a number of panels in the World Climate Research Program and was a lead author of the 5th IPCC assessment reports and a coordinating lead author on the 6th report, which is the one we're talking about today. Next, we have Professor Benjamin Houghton. Professor Houghton is the director of the Earth Observatory of Singapore at Nanyang Technological University, where he's also professor at the Asian School of the Environment. Professor Houghton's research concerns sea level change with the aim of understanding and integrating the external and internal mechanisms that have determined sea level changes in the past and which will shape such changes in the future. Professor Houghton was a review editor of Chapter 9 of the report about ocean, cryosphere, and sea level change. Next, we have Professor Josep Canadell. Professor Canadell is Chief Research Scientist at the Climate Science Center at the Commonwealth Scientific and Industrial Organization, CSIRO. He was a lead author of Chapter 5 of the IPCC report. And finally, we have Dr. Junyi Lee. Dr. Junyi Lee is Associate Professor at the Research Center for Climate Sciences at Pusan National University. She is also affiliated with the Institute for Basic Science Center for Climate Physics, and she was a lead author of Chapter 4 of the report. So as mentioned by Elle at the beginning of this session, we will first start by having a short presentation by each of our panelists. And please, participants, either type your questions in the chat function or keep your questions for the end of this, after the talks. We will be taking questions. So first, I would like to welcome Professor Thorne for his presentation. Thank you. Professor Thorne, the floor is yours.
Thank you very much, and hopefully slides will come up shortly. Waiting to see whether the slides come up. If there are no slides, I can start talking to it. Okay, here are the slides. Great, I can see them. So I'm going to talk about Chapter 2, on which I was coordinating lead author. And I'm going to talk about, the chapter was really about observational change, and that includes both direct observations with meteorological instrumentation, including satellites and upper air, but also looking back into the proxy record, going back as far as we can. And the fundamental headline from this is shown here, that recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. So we can go to the next, please. So I'm going to talk you through this figure that you can see here, which is from the summary for policymakers. It's part of a figure, in fact. It's the first half of figure SPM1. And it's really pointing to the unusualness of what we have seen in terms of surface temperature. So the parameter that is plotted here is global surface temperature. You can see going back, this goes back over the Common Era, the past 2,000 and a bit years. You can see in the main panel here, you can see a long bluey gray kind of shaft, if you like, of a hockey stick. And then you see that combined with black at the end, which goes up almost vertically. So what is this? Well, the black that you can see here is the observations. They've been smoothed in the same way as the reconstructions. It's important to note that the reconstructions are decadally resolved. This is a reconstruction from proxy evidence of climate, of the changing climate. And you can see that for about 2,000 years at least, the climate has bounced around. It cooled a little bit through to 1850, and then it went up very, very quickly, both in the proxies and the observations. So the warming that we see today is fundamentally unusual in at least the past 2,000 years. Now we can go back even further, and we can look back with coarser resolution, centennial resolution reconstructions, and we can look at what was the warmest period in the present interglacial, the Holocene. That was about 6,500 years ago. It was forced by orbital forcing, solar forcing. Our reconstructions of that are greatly improved compared to the fifth assessment report, We can put bounds on them. So the very likely range is 0.2 to 1 degree. Well, we're now in the last decade at 1.1 degrees. That means arguably we have moved the climate system outside the safe operating space of which we have developed from hunter-gatherers through an agricultural revolution, an industrial revolution, a technological revolution. To go back, and this is where, to go back to a time when it was last plausibly as warm as today, you would have to go back to the last interglacial, the peak warmth of the last interglacial, when sea level, for example, was between 5 and 10 meters higher than today. So next, please. So we don't take the assessment just on the basis of surface temperature. I've shown you in detail surface temperature. What I just want to get across here is that we look across the atmosphere, we look at air temperatures aloft, we look at water vapor, total column water vapor, surface humidity, we look at atmospheric circulation, we look in the frozen part of the planet, we look at the cryosphere, and we look at permafrost, we look at ice sheets, we look at snow cover. We looked uniquely this time at the biosphere. We looked at evidence for greening. We looked at evidence for changes in the seasonal cycle of carbon dioxide, the growing season length, phytoplankton changes in the ocean. We also looked at the physical ocean, sea level, ocean heat content. Now, each of these individually is a single piece of evidence. It could be questioned. The real power is when you bring these all together. All of these lines of evidence are coming together and telling a coherent story of a world that is rapidly warming. And when we look at the paleo context, when we look at the long-term context, all of these are unusual on timescales ranging from multiple centuries to multiple millennia to, in the case of CO2, millions of years. So we really are entering uncharted territory in the climate system. Our evidence of that climate change is multifaceted. It's multiple parameters across the atmosphere, the ocean, the biosphere, and the cryosphere. They're highly unusual, and it's not down to a single data set, a single estimate, a single group. This is multiple scientists looking at these things, proverbially looking at these, kicking the tires on our scientific understanding. And it's the robustness of the multiple aspects of the climate system that change coincidentally that really gives us the strength to make the conclusion that we make, that climate change is unequivocal, the warming is unequivocal, and that it is highly unusual in the context of at least many thousands of years. We really are moving the climate system in important and fundamental ways. And I will hand the floor back at that stage, please.
Thank you very much, Prof. Thorne. Indeed, we could see a lot of data sets, a lot of data are changing very quickly. It's unprecedented, uncharted territory, to use one of Prof. Thorne. So today, I think we're going to learn more about all these different processes that are driving such changes. So next, I'd like to welcome Dr. Raghavan for his short presentation. Dr. Raghavan, the floor is yours.
Thank you very much. Today, I will be presenting some of the key assessments from the water cycle chapter. This is chapter 8 of the AR6 Working Group 1 report. We had 3 coordinating lead authors and 13 lead authors and 48 contributing authors. Can we go to the next slide, please? This is a process-based chapter. Can we go to the next slide? Yeah. Here we assess the different components of the water system, the exchange of fluxes across the different components. And as you can see that the oceans are occupying almost 96-97% of the, they contain the water source, that is the main source of the water. And basically the saline groundwater and lakes, the saline waters contribute about 1.61% of the total water stores, and surface freshwater is only 1.8% globally. And what is really available, because much of the ice and snow and glaciers is not accessible to human. So only a very small 3% of the terrestrial freshwater is available to human consumption. So human activity. So it's a very scarce commodity. So climate change affects different components of the water cycle. Next slide, please. And we also assess the exchange of fluxes, water fluxes across different components. The ocean is the main component. The evaporation from the ocean is the main contribution for precipitation, both over land and oceans. And especially this is very important for the monsoon regions of Asia, monsoon regions of the world. And we also assess the exchange of fluxes from land, from also the river discharge and so on. Next slide, please. Yeah, I'll just read some of the key assessments. This is for the current state of the climate system. Human-induced climate change is already affecting weather and climate extremes and also the water cycle components. And we are seeing heavy precipitation, droughts, tropical cyclones, which are all elements of the water cycle. And each chapter in the AR6 has an attribution to the human influence, and this has strengthened since AR5. And possible climate futures with continuing global warming, the global water cycle is projected to intensify in the future. Not only the mean water cycle will intensify, also its variability. The global monsoon precipitation will also intensify, and also the severity of wet and dry events. Next slide, please. This chapter, as I said, we have assessed multiple lines of evidence to understand what happened in the past, what is happening in the present, and the effect of the human influence, and what is projected in the future. And water cycle changes involve multiple drivers. And we have different topics. We have focused on key topics. Some of them I have highlighted here: the evapotranspiration, global water cycle intensity, the IPCC and tropical rain belts, monsoon, precipitation, runoff, stream flow, flooding, soil moisture, aridity, water vapor and its transport. I will focus on monsoons, which is very special, highly policy relevant for Asia. Next slide, please. As my previous speaker highlighted that the recent changes that we are seeing since pre-industrial times is the human influence is unprecedented. And this warming, what we have seen since the accelerated warming since the 1950s, cannot be explained just by natural variations. So the human influence through greenhouse gases is very, very fundamental. But what we also see in the important thing is there are natural forcings like volcanic eruptions, which can throw a lot of aerosols which can enter the stratosphere, and they can produce episodic cooling globally. And this is very important for the water cycle changes, and it can also affect El Nino events and so on. Next slide, please. And also other point is observed warming is driven by emissions by human activities with greenhouse gas warming, partly masked by aerosol cooling. This is a very important message because water cycle changes are not only responding to the greenhouse gas forcing, but also due to anthropogenic aerosol forcings. Especially we see that if you had only the greenhouse gas warming, the observed warming would be about 1.5 due to the greenhouse gas forcing. But aerosols, especially the sulfate aerosols in the northern hemisphere, they have caused a cooling of about 0.4. And this has especially implications for the water cycle. Next slide, please, and the monsoons. And this is a paper which highlighted that they showed the fingerprint of the greenhouse gas forcing and the aerosol forcing on the global and regional precipitation and temperature changes. We can see the greenhouse gas forcing fingerprint has a a strong fingerprint in terms of the warming globally, with stronger warming in the polar regions and the mid-latitudes, and to a moderate extent over the tropics. And many regions you can see increased precipitation. But when you see the aerosol fingerprint, you see a north-south asymmetry. Because of the emission loadings are mostly predominant in the northern hemisphere. So you can see a strong cooling signature in the northern hemisphere. And there's a pattern of warming to the south of the equator in the southern hemisphere. And studies have shown that if you have this interhemispheric contrast in the radiational input, in the energy input, it tries to shift the IPCC to the south of the equator. So normally many areas in over Asia or West Africa, so the aerosol fingerprint leads to precipitation reduction. And whereas the IPCC shift to the south, and you also see the fingerprints in terms of the aridity changes. Next slide, please. And we have assessed in the AR6, we have assessed different regional monsoons, which are different from the definition of monsoons in the AR5. We have 6 regional monsoons. And what we have shown, these are the observed trend in the precipitation from 51 to 2014 for North America, West Africa, South Asia, and East Asian monsoons. What we find is, I'll just focus on the Asian region. In the South Asian region, there has been a decline in the precipitation by about 6-7% during this period. And this is basically explained due to the combined influence of both aerosols and greenhouse gases, where aerosols have tried to decrease the precipitation. On the contrary, the greenhouse gases are trying to enhance the precipitation. So the historical simulation, all forcing experiment shows a declining trend. And this is all, and we see a similar signature, the contrasting effects of the aerosol and greenhouse gas forcings over the East Asian monsoon and partly over the West African monsoon, which is also associated with interdecadal variability. Next slide, please. With regard to the future projections, we find that as with continuing global warming, monsoon precipitation is projected to increase over South Asia and East Asia in the mid and the long term. In the near term, there are uncertainties due to the internal variability and natural forcings. Next slide, please. So basically, one key message is we see the combined influence that the decreasing trend of global land monsoon precipitation from the 50s to the 80s is partly attributed to human-caused northern hemispheric aerosol emissions, but increases since then after the 80s have resulted mainly from rising greenhouse gas concentrations and decadal to multi-decadal internal variability. And over South Asia and East Asia and also West Africa, precipitation increases due to warming from greenhouse gas emissions were counteracted by decreases in precipitation due to cooling from human-caused aerosol emissions. For the future, a warmer climate will intensify both wet and dry weather and climate extremes and seasons, events, and with implications for flooding and drought. But the location and frequency of these events depend on projected changes in regional atmospheric circulation, including monsoons and mid-latitude storm tracks. This is my last message. Monsoon precipitation is projected to increase in the mid to long term at a global scale, and particularly over South and Southeast Asia, East Asia, and West Africa, apart from the far West Sahel. This is a high confidence statement. Next slide, please. Next slide. Oh, thank you. I'm done with my. Thank you so much.
Thank you very much, Dr. Raghavan. A very insightful presentation about the effect of climate change on the water cycle, which is already affecting basically the water cycle and will continue to affect it, including the intensity of monsoons and the intensity of extreme events. So thank you very much, Dr. Raghavan.
Thank you very much.
The next presentation will be given by, the next presentation verbally will be given by Professor Ko, who is here with me today. So Professor Ko, please.
Thank you, Laurian. I didn't prepare any slide today. mainly because I think as a discussion forum, it's good to engage people verbally. It's not uncommon for discussion forum for me to react spontaneously to what people said. But of course, having said that, I have prepared something in my mind. Well, just a brief introduction. I'm Tae Yong Ko, and my specialization is in atmospheric sciences, particularly in the dynamics. So I must confess that I have not read the thousands of pages of the report in this AR6. I have not been involved in any way in the AR6 process, so I'm not a lead author, I'm not a reviewer. Although I was involved in the predecessor report, the AR5, as an expert reviewer. But even then, I picked the chapters that I like on modeling, that sort of things, to review. So this is the limit of my knowledge, one can say it that way. So at first I was wondering why was I in this session, which is actually mainly about AR6. Then I realized that, I'm an atmospheric dynamicist, and that's how they describe me. And I suppose it's the atmospheric dynamics angle that I contribute. And why is it important to look at atmospheric dynamics? Many times in today's atmospheric science world, computer modeling is an essential tool to get some kind of predictions about what will happen in future under climate change. And then atmospheric observations, remote sensing and in situ measurements are also paramount to provide evidence to support or to refine those models. But what seems to have been somehow slightly overlooked by the general population of scientists is dynamics. Understanding what the models do, making sense of the observations. Sometimes I get an impression in public seminars that it's always easier to show plots from computers or analysis from observations, and then from that picture, describe it. There will be more rainfall. Oh, it will be hotter. There will be drier weather ahead. State it as though the picture is all there is to it. And then the listener, whether public or sometimes scientists who are not in that specialization, will just take it at the face value and accept it. But actually, we are doing science. So what is crucial in this enterprise is understanding and that agreement with that picture that arises from understanding. So I think that's why I'm here. I'm here to maybe shed a bit of the dynamical understanding. So I think I'll point out, I'll mainly talk about one thing, since we're in Asia Oceania Geosciences Society, right? So the Asian-Australian monsoon is a big thing for us. I happen to serve in the Asia-Australian Monsoon Working Group under the auspices of the World Meteorological Organization. So it's one of my interest topics as well. And the last presentation you saw, the prediction, when you run models to equilibrium with higher greenhouse gas emissions and with the various scenarios for aerosol emissions, the net result is that in the long term, the monsoon system over this region will intensify, essentially. You have greater temperature contrast between land and sea. The land heats up more than the sea, obviously, because of the different thermal inertia. As a result, pressure over land will in the future be lower, and pressure over sea will be higher. And that drives a stronger low-level flow towards the land. And that brings more moisture to the land. And therein, the presence, the enhanced moisture content over land is the one that destabilizes the atmosphere, leads to small disturbances up and down. That is the one that creates the rain, the up and down motion, which we call convection. I must make a very sharp distinction here, because commonly people will explain this is in this slightly different way. Oh, you have more moisture converging over land, hence there's more rainfall, right? Hence there's more rainfall. If you think about it mathematically, it's an equation. On the left-hand side, you have convergence of moisture. On the right-hand side, you have the production of rain. And the two, of course, in a model must balance. Otherwise, the water substance will not be conserved. But because the equation is written left-hand side equals right-hand side, one might always tend to read left-hand side is the cause, right-hand side is the result. But an equation itself does not imply that at all, because you could have written it the other way. Swap the left-hand and right-hand side. So you could have also said that the increased rainfall drives the stronger convergence. So this picture is not making any statement about cause and effect. So you cannot explain this as convergence of moisture leading to more rainfall. That doesn't make dynamical sense. That is misinterpreting an equation. An equation, left, right are equal in all aspects, and there's no information about conceptual causality per se. So I phrase it very carefully. I say destabilization of the atmosphere. So the fact is that you do have higher moisture content over land. So what happens? Where's the causal link? This is where concepts come in. When you have more moisture over land, the potential instability in the vertical column is higher. So when you have random stochastic disturbances, there will be up and down motion leading to cloud and then rain formation. So it is an increased instability that makes it easier to form rain. So this is the dynamical understanding of what is happening. And I also must emphasize that it is not a simple case of, oh, in the future world, there's higher temperature, hot air holds more moisture, and more moisture means more rain. Again, that understanding is, strictly speaking, not right. Otherwise, you can't explain why would there be a drier area when the temperatures are getting higher, because you said there will be more moisture. So the atmosphere does not work in those simple ways. A deep understanding of dynamics is important to interpret the results, and then that is the root of our scientific confidence in the result. So with that, thank you very much for your attention. I pass the mic back to Lorian. Thank you.
Thank you very much, Prof. Ko. A very insightful perspective on the importance of understanding what we put in the models. An equation is only an equation. To determine causation, we need to understand the processes. Thank you very much. So next, I'd like to welcome Prof. Bisbeck, who's going to talk about, so his presentation is entitled Ocean-Related Climate Change and the UN Decade of Ocean Science for Sustainable Development. Prof. Bisbeck.
Yes, Lauren, thank you very much for inviting me to the stage here, and I really want to thank the Asia Oceanic Geosciences Society for having me here, in particular my good friend Robin Robertson, who is the Secretary General of that. And what I'd like to take you on a journey is from the climate assessments that we're discussing here into what one might call the solution space, and I'm going to focus on the ocean. Next slide. Now, the assessment report, the one that we're discussing here, can we have the next slide? The one that we're discussing here, it makes a couple of central points. And I took this graph actually from the special report on the ocean and cryosphere, which shows you the connectivity of the ocean, the atmosphere, and the cryosphere, and how they're affecting the climate. Some of the highlights that are no news to many of you here on the panel, but also listening, is that the ocean has a very central role in the climate system. A couple of examples: it has taken up 93% of the extra energy that we, by burning fossil fuels, have amassed in our climate system. And again, 93% go into the ocean, which then mitigates or moderates the warming that we see in the atmosphere, the sphere that we live in. It also has taken up about a quarter of the CO2, and these have leads to changes in the ocean system, like warming, like sea level rise. We're going to hear about a bit in a moment, but also chemical changes like ocean acidification, loss of oxygen, and the like. But what I like to take a different tack, and on the next slide, let me just show you how we in the sciences deal with that. Next slide. So in the sciences, in ocean sciences, climate sciences, a lot of us, and in this panel, we're discussing a lot the pressure that human activities exert on the environmental system, the ocean system, the climate system. Now, these are important sciences, and we are urging maybe the population to take note of these pressures and maybe deal with them. But I want to show on the next slide that that's not the only thing we do. Because some of us, next slide, please. Because some of us are also doing science on thinking about how to support resilience. And resilience is important in the climate side on the solution end. How can we build up societies or environment that becomes resilient or can adapt to climate change? Next slide. And the reason why we do it, I think we have in mind that we really want to elevate the prosperity of humanity, which benefits from a stable climate, but also benefits from the ocean and maybe a sustainable use of the ocean. So it's this combination of understanding the climate system, how it's changing, and then the lessons that we're learning out of that. Next slide. And that is where the connection comes in to the 2030 Agenda for Sustainable Development with the Sustainable Development Goals. And I want to mention here that Goal 14 focuses on the ocean, on the human-ocean interactions, and the Goal 13 focuses on the climate, which is what we're discussing here a lot. But so an understanding of the climate system, the ocean system, should inform our actions for sustainable development. Next slide. Now, realizing that and realizing that the ocean is not the main sphere of the environment that most people, in particular in policy circles, think about, the UN General Assembly has proclaimed, starting this year, a whole decade of ocean science in support of sustainable development. In short, the Ocean Decade. And it is a decade that really elevates the science that we need, the ocean climate science for the need for the future, for the ocean, for the environment that we want. And it really supports transformative sciences, the science that enables to change behavior. And I think this is what the IPCC calls for. It gives the evidence base upon which we're invited to act. Next slide. And it shows you a political perspective on this Ocean Decade. And I just want to share a couple of minutes on the high-level launch of that decade. It happened in virtual Berlin last June.
The ocean acts as a climate machine, economic space, and a source of food for many, many people around the globe. And I would like to invite all of you to join us for a dive into the unknown secrets of the ocean.
The future of our Earth thus heavily depends on how we treat our oceans. Germany has proved itself to be a competent and reliable partner in this field.
We need to start living in harmony with the ocean.
It is time for a revolution in ocean science. And this revolution now has a name: the United Nations Decade of Ocean Science for Sustainable Development. Together, let us discover the science we need for the ocean we want.
This decade offers a unique opportunity, a clear framework for action by better coordinating global efforts.
We are very much aware that to reach our European Green Deal ambitions and make Europe a climate-neutral continent by 2050. We need healthy oceans.
The agreed ambition of the G7 to tackle climate change, which of course is such a stressor on the ocean system.
The ocean is our future.
It's become increasingly obvious that ocean science must be the foundation upon which the achievement of SDG 14 is built.
I can tell you that we do not have time. We have to act now.
There's a lot of traditional knowledge in our region built up over millennia that we could make use of in the global science community.
You have to think 7 generations ahead.
Ancestors preserve food through a process which they call ra'wi. So in certain places when they fish, for example on the reef itself, there is a section that they have to block, which is taboo, that no one's touched it.
We need international organizations and we need the willingness.
Can we go to the next slide? So there's a wonderful film that I can really share with you on YouTube. But this decade of ocean science for sustainable development has identified 10 challenges, which I won't read all of you. It's about pollutants, biodiversity, feeding the world, and the ocean economy. Next slide. But one of the areas really enhances an understanding of the ocean climate nexus, which I think is most relevant for this discussion here. And you see that that ocean decade really is the avenue to take some of the recommendations from the climate assessments towards actions. And I think that is what an exciting frame that we should be also discussing here. Next slide. And there's certainly another element that is around capacity development and equitable access to data, information, knowledge, and technology. And the next slide shows you one of the opportunities which I think are ahead of us. As we have more information on the ocean from observing systems, from climate models, ocean models, I think it allows us to build up what we call digital twins, digital replicas of the climate system, of the ocean system, that can help us to inform society on their actions, on testing solutions, on thinking of what's to come. Next slide. And to advance this, we're advancing a program that we call the Digital Twins of the Ocean, DITO. It's an activity as part of the UN Decade of Ocean Science for Sustainable Development. And what it tries to do is it build out that digital framework, the tools, technology, the sharing of the information to really allow regions, actors, stakeholders to build their own digital twins of a part of the ocean, of a part of the climate system, to really look for solutions, to look for new science, new understanding. And I think these are exciting opportunities to combine the digital revolution that we see in science with an understanding of the climate system, of the ocean system, but actually enabling solution-oriented science, which I think is what we need to address the challenges ahead of us. So over to you and back to the panel discussion. I'm looking forward to discuss that more deeply.
Thank you very much, Prof. Wisbeck, for this very inspiring presentation about the importance of preserving oceans for sustainable development and also the call to take actions now. And that's very nice that you had these last slides about your project. So we are midway in the presentation, so I'd like to remind the online audience to type any questions you have in the chat, and for you in-person audience, keep them in mind for the end of these presentations. Thank you. So next, I'd like to welcome Prof. Doblas Reyes for his presentation about producing regional climate information. Professor Doblas Reyes, the floor is yours.
Thanks very much, Lorianne, and thanks for the organizers, for inviting me to participate in this very interesting event. Next slide, please. So I'm going to talk about one new aspect of this, of the Working Group 1 6th Assessment Report. Next slide. Which is the inclusion of a significant amount of regional climate information in the report. This is a big difference with respect to AR5. In AR5, in Working Group 1, there was already quite a substantial amount of information relative to climate change at the regional scale, but I think having participated in AR5 as an author, that what has been achieved in the sixth assessment report is really one order of magnitude richer and more complex. I would like to pick on one of the words that Martin already mentioned, which is this solution-oriented research. And somehow, for the first time in Working Group 1, we have integrated into the narrative of the report the idea of why we are providing this information and this what for we are synthesizing all this information, in particular at the regional level, has been made explicit by introducing the concept of the distillation of the climate information. With this, what we mean is that somehow the climate information is not produced by physical climate scientists for a receiving end made of users from a really wide variety of sectors that are climate sensitive, but it's a co-producing process in which both the values and the context that is relevant for the generation and the use of this climate information should be taken into account and made explicit. And by values, I don't just mean the values of the users, but the values of the scientists that are generating the climate data that are at the origin of the climate information. And this is easier said than done, because traditionally in physical climate science, we haven't made explicit those values, the way we make decisions on what climate problems we consider are important, and even how we make decisions on the design of the experiments that we performed. And there is a lot of very interesting literature that we have assessed in these reports that has been integrated into the production of this regional climate information. Next slide, please. So this is a very complex process. It's that involves the use of a wide variety of sources of climate data and climate knowledge that is synthesized into climate information that is actually used in a parallel process of discussion with the users of this information. The most important aspect of the generation of climate information is that it's an iterative process. It's not that the physical climate scientists produce a few plots and they transfer them to users, but that those initial pieces of information that could take the form of data, plots, or even narratives is co-produced and modified in continuous discussions with those users. Next slide, please. The variety of sources of regional climate information is briefly and very simply illustrated in this figure, which is taken from Chapter 10 of the Working Group 1 sixth assessment report, where one can, for the case of the precipitation in South Asia, one can see the complexity and the variety of sources that have to be taken into account when producing the relevant regional climate information. And this is even before we start the interaction with those users. So this includes observations, simulations, the attribution of these observed and future signals to human activity, the use of large ensembles of simulations, and the contrast between past and current climate experiments, plus the access to local expertise. Next slide, please. All this has been put in practice in the report, where you can find a huge amount of regional information in assessments that have been performed without borders, and that has followed the 4-step procedure that appears here, that consists in collecting the lines of evidence, in assessing those sources of information, in documenting them so that there is full traceability of the information that is produced, and in synthesizing all this information to messages that can be easily accessible by those that have requested the report, in particular the governments that are part of the IPCC process. And all these steps have been put in practice in the production of a number of regional fact sheets that can be found in the IPCC Working Group 1 AR6 website, and that for which you can find the link in the slides. Next slide, please. And this is going beyond the simple understanding of regions as a subcontinental areas, and it really goes into other types of regions that are less typical, like, for instance, urban areas. And understanding that by 2030, almost 60% of the world's population is expected to live in cities. Next slide, please. The report has put a lot of emphasis into the understanding of the climate change at the urban scale. And this is an oversimplification, because these are the conclusions that are that are general for most of the large urban settlements around the world, that where, for instance, we have looked into the impact of climate change in terms of temperature, in terms of the precipitation, humidity, and the impact of sea level that is actually being influenced or being combined with the impact of precipitation to increase the risk of floods in coastal urban areas. So this is just to say that addressing the production of regional climate information is a very complex process, but that for once the physical climate science community has become aware of how important it is to engage with other communities to make a difference and to produce user-relevant climate information. And that's all. Thanks very much. And back to you, Lorianne.
Thank you very much, Prof. Dobrastra. Yes, and thanks for this very useful presentation about what goes behind these fact sheets that I personally found very, very useful, that we can download from the IPCC website. So thanks for explaining the complex integration of different sources of information to produce this data. So next, I'd like to give the microphone to Prof. Horton. He'll be talking about sea level rise.
Good afternoon, everyone. Thank you, Lorianne. Thank you, AOGS, for inviting me to talk today. So I'm going to talk about the chapter that I was involved in, which is regarding sea level rise. So you may or you may not know that the IPCC consisted of over 240 scientists, and they reviewed over 14,000 pieces of literature for which to make their recommendations on the future state of the climate. But when you delve into detail, for Chapter 9, for example, the review of the ocean and the cryosphere to provide projections of sea level, was down to just approximately 20 scientists, for which I was one of them as a review editor. Now, this group of 20 scientists had to address a complex problem. Sea level rise is a complex problem because there are a variety of driving processes that you use to project future sea level rise. They're global, they're regional, and they're local, and they operate at different spatial and temporal scales. At the global scale, we have two animations. At the bottom right-hand corner is an animation showing the process of thermal expansion. So if you increase our ocean temperatures, our oceans occupy a greater volume because the water molecules expand and sea level goes up. And this process has been responsible for around 50% of the sea level rise in the 20th century. The second dominant process is a mass problem. So if you increase atmospheric and ocean temperatures, the land-based ice on our planet, glaciers, ice caps, and ice sheets melt. Through the hydrological cycle, it's transferred into our ocean basins, and sea level rises. In the 20th century, the dominant contributor were our glaciers. In the 21st century, worryingly, it's our large ice sheets. Greenland and Antarctica together have the potential to raise global sea levels by 70 meters. That's how much water they have within them. When you get down to the regional processes, and this was a significant advancement on the IPCC, which was briefly introduced by Francisco in the previous presentation, you have a variety of processes. On the top right-hand corner, we have a process known as glacial isostatic adjustment. This is a change in the height of the solid Earth in response to extinct ice sheets. 20,000 years ago, there were two large ice sheets, one in North America and one in northwestern Europe. If you were underneath the ice sheet, the land subsided. If you were at the margins of the ice sheet, the land uplifted. When that ice sheet melted, it changed vertical land elevations. At the bottom right-hand side, we have a process related to the gravity of the Earth. Our current ice sheets in Greenland and Antarctica are very large in mass, so they attract water to them. If these ice sheets lose mass, the fingerprint associated with the gravity changes on our oceans, and you get greater sea level rise at regions distal from the ice sheets, such as the tropics here in Singapore. But there is still much that we have to learn. The IPCC is aware that there are a variety of processes at the local scale, which are very significant here in Southeast Asia, that are either poorly constrained or not accounted for. For example, in the top right, we show land substance due to groundwater withdrawal. Many of the cities in Asia take significant amounts of water from coastal aquifers for agricultural, residential, commercial use. Removing of that water causes the land to sink. Here in Southeast Asia, we have one of the most tectonically active regions in the world. And in the bottom right shows an animation that the land heights change both during and within earthquakes. And finally, on the left-hand side, we have a process related to ocean dynamics. We have a very, very complex geography here in Southeast Asia, and the ocean dynamics related to wind or ocean currents is poorly constrained. So now I'd briefly like to show you some of the projections from the IPCC's report. I'm going to show projections for the low emission scenario, in blue here, the SSP 1, 1.9, and a high emission scenario, which is SSP 5, 8.5. So the graphic shows the median, or the 50th percentile, running from 2020 out to 2100. In the table show what the IPCC calls the likely range, from the 17th to the 83rd percentile. This graphic shows what you expect, a significant difference in the magnitude of sea level rise between a low emission, around 40 centimeters, and a high emission of around 80 centimeters. If we look at the 83rd percentile, it's around 1 meter, which is very similar to the values that were produced by the 5th assessment report. But as I said, an advancement in the 6th assessment report is to look at the regional scale. So these are the projections for Singapore. we can see that the median, or the 50th percentile, is near identical to the global mean, differing by a centimetre or so. But if we look at the 83rd percentile, we have around a 20 centimetre increase at around 1.18 metres. Now, if Singapore is around the global mean, there are other places on the planet that are significantly greater or significantly less. Oslo in Norway, a much diminished sea level rise. At the 50th percentile under the low emission, there's no net change. Why is that? Well, that's because this region was underneath a large ice sheet 20,000 years ago, and the land has been uplifting at the rate that the oceans are rising. Conversely, New York City is greater than the global average. Again, why? This is because New York City was at the margins of the North American ice sheet, uplifted 20,000 years ago and continuing to subside. But then we have regions such as Manila, far, far greater than the global average. And that is because of local processes such as groundwater withdrawal. The IPCC also included what are called high impact, low likelihood events. These are events that have a possibility of occurring in the 21st century because we know the process, we know they've occurred in the geological history, but we don't know exactly when they're going to occur. And regarding sea level, it's associated with a disintegration of the Antarctic and the Greenland ice sheet through two processes: marine ice shelf instability, where the ice shelves that protect our oceans from land-based ice, in particular in Antarctica, disintegrate, and marine ice cliff instability, which occurs when that disintegration of the ice shelf causes catastrophic cliff falls into our oceans. So just to finish up, I just wanted to show you what the impacts of those events would be here in Singapore. So here we show a comparison of the high impact, low likelihood versus the high emission scenario. And we can see a 20 centimetre or so increase for the 50th percentile, but a 50 centimetre increase to 1.75 metres by 2100. And then to finish and to leave you with, these processes are more likely to occur in the 22nd century, and their contribution will be greater. If we look at the 83rd percentile for 2150, the magnitude of the rise is over 5 meters. The Prime Minister of Singapore said that sea level rise was an existential threat. A disintegration of the Antarctic ice sheet is the existential reality to island nations and low-lying areas throughout the globe. Thank you.
Thanks, Prof. Horton. It's a bit hard for me to speak after such inspiring words, or worrying words, I should say. Thanks for highlighting and shedding lights on all the processes driving sea level rise. They are very complex, but indeed there is a lot also that we know. And I think one important message is to, although there is an increase in global sea levels, it's extremely important to look at local processes and local sea level, because they can vary by a lot, as we saw in the presentation. Thanks, Prof. Horton. Next, I'd like to welcome Prof. Canadell for his presentation entitled Climate Change, UN IPCC AR6.
Thanks for the opportunity. And what I'll be discussing is just showing you some of the highlights of Chapter 5, which was on carbon and biochemical climate processes. Next, please. So an IPCC presentation cannot be without one of these classic figures in which we show that current carbon dioxide concentrations are higher than any time, at least in the past 2 million years. But the reason I'm showing you this figure, which there's no novelty to this audience, is because I want to show the next one. Next one, please. And that is, next one. And that is because equally important that the uniqueness of these very high atmospheric CO2 concentrations is the velocity of change of these concentrations. So if we were to look at the rates of increase of carbon dioxide concentrations during the industrial era, that is the last 200 years, are 10 times faster than any time in the last 800,000 years. And they're 4 times to 5 faster than any time in the last 56 million years. I must say that there is, of course, a resolution issue in which we usually talk about the last 800,000 years being the fastest now in chunks of 100, 200 years. So we don't have resolutions of annual as we have it now. And for the 56 million years, we do look at big chunks of at least 1,000 and more, in which we have not seen any acceleration as we've seen it now. Next one, please. Now, the reason this is important, of course, is because both the actual perturbation of the carbon cycle, it is unique in ways that almost we have no paleo record analog. And there's no better evidence for this acceleration of the anthropogenic perturbation of the carbon cycle than showing this figure that it shows the 6 assessment reports of the IPCC, the first one published in 1990, the last this year, during which 30 years we have emitted 1 trillion tons of carbon dioxide. That is 41% of all CO2 emissions from the combustion of fossil fuels and land use change emitted, since, as I said, 1990, and out of 271 years expand in different way to actually look at this thing is that since 1990, 2/3 of the carbon budget for stabilizing the climate at 1.5 degree has been consumed. Next one. The most remarkable thing is that that despite this increase of anthropogenic emissions, the diagnostic that we call the urban fraction, that is the fraction of the total anthropogenic emissions that stay in the atmosphere, has been relatively stable at about 44%. That is, for every ton of CO2 we put into the atmosphere, 560 kilos are removed by the natural CO2 sinks from land and ocean, and the rest remains in the atmosphere, creating climate change. Next one. However, despite this stability that I just showed from the contemporary in the past, we know that when we look at the different scenarios of different emissions pathways from left to right, from the 1.9, 2.6, which are consistent with the Paris Agreement, all the way to the SSP 8.5, which will reach temperatures at the end of this century anywhere between 4 and 5 degrees. The total amount of emissions increase dramatically, of course. That's what drives that warming. But importantly, the amount of sinks also increase, so that the size of the colored bars increase from the light blue all the way to the dark red, indicating the perturbation of the climate by those additional emissions. However, the fraction of those emissions that are removed by the natural sinks on land and ocean diminishes from the very low 1.9, let's say under 1.5 degrees at the end of the century, all the way to the 4 or 5 degrees at the end of the century in the 8.5, it continues increasing from 70%, that's the number inside of the donuts, all the way to 38%, being perhaps one of the most compelling reasons for why we want certainly to try to stabilize the climate at these lower levels where we have the most help from nature. Next slide. Now, part of the issue is what we call the biochemical climate feedbacks, and that is because these anthropogenic emissions of CO2, methane, and N2O, as we've seen in these three panels, are embedded into a natural background sources and sinks, which are part of the natural process. They interact with the changing of the climate and create, the feedbacks that we often discuss. Next one. Next one, please. And this is a good representation and summary of the big effort that we put in the IPCC to assess the direction and size of many different really important biochemical climate feedbacks. And just to kind of look at some important ones, it might be a little difficult to see on the screen, but if you look at the third panel below, there's responses, there's fire, we have large uncertainties, we have CO2 emissions coming from the permafrost, we have tremendous large uncertainties, which kind of points out places where more research is needed. This, what we're seeing here is the reinforcing per degree centigrade change that we expect from these various processes. So on the right side will be emissions, on the left side would be a cooling effect. And look at some of the uncertainty ranges, which are really big, from significant quantities that can potentially change quite a bit the net reinforcing due to all these feedbacks, which is, kind of screams for a lot of new research further. Next one, please. And I'll just go to the next one, just to almost finish now. And just to kind of, finish saying that quite a few of the feedbacks that I show you before for the first time have actually gone into the assessment of the remaining carbon budget. The remaining carbon budget is how many more emissions you can still emit into the atmosphere before you reach a particular climate level, 1.5 at 50% probability. You still have 500 gigatons, billion tons of carbon dioxide that you can still emit. Next one, just to finish. So if we were to translate these remaining carbon budgets, and we were to look at, the emissions that we had of CO2 in 2019, so for the 1.5 at 50% probability, at the same rate of emissions in 2019, we would have 12 years remaining before it gets completely exhausted, or 32 years for the 2 degrees, which is a much bigger. And that's actually quite consistent with what we expect, in terms of reaching the 1.5 degrees early into the next decade. So I'll stop here. Thank you very much.
Thank you very much, Prof. Canada, and this presentation about the carbon budgets and biochemical climate feedbacks. So the last speaker of today is Professor Lee, who's joining us virtually, and she doesn't have a slide, but she's going to talk about her key messages on future global climate from the IPCC AR6 report. Professor Lee, thank you.
Thank you very much for having me here today. I am in the same page with Professor Cole, and I will talk without slides. I'd like to take this opportunity to address 4 questions mainly relevant to key findings in Chapter 4, where I have served as a coordinating lead author. The first question is what the big science advances are in this report. Among many important science advances in this report, I'd like to talk about 4 aspects which are relevant for estimating our climate futures. The first big science advance in this report is the improvement made in the estimation of climate sensitivity, which measures how the climate system responds to emissions of greenhouse gases. Improved knowledge of climate feedbacks, past climate states, and the observed energy gain have led to a reduction in the long-standing uncertainty in equilibrium climate sensitivity. The previous likely range was from 1.5 to 4.5 degrees Celsius, but in this report, we provide the new estimation with the likely range from 2.5 to 4 degrees Celsius. The second advance is that climate models used in this report have been improved as compared to models considered in the previous report, including new and better representation of physical, chemical, and biological processes, as well as higher resolutions. This has improved the simulation of the recent mean state of most large-scale indicators of climate change and many other aspects across the climate system. However, it is also important to note that the CME6, the current models, shows a higher average climate sensitivity than the previous version, mainly due to amplifying cloud feedback. Third is the methodological advance in refining projections of global warming based on how well models simulate past warming in addition to clearer insights from observation and theory. Last but not least is that for the first time in the IPCC report, we provide a comprehensive assessment of future changes in global surface temperature, ocean warming, and sea level. We combine multi-model projections with observational constraints, as well as the new estimation of climate sensitivity I just mentioned. The second question is whether we can stop further warming. Whether we can stop further warming or not is in our hands. Limiting further warming requires immediate, rapid, and sustained reduction in carbon dioxide, methane, and other greenhouse gas emissions. This would not only reduce the consequences of global warming, but also improve air quality. With rapid reductions of greenhouse gas emissions and targeting to reach net zero carbon dioxide emissions around 2050, it is extremely likely that global warming can stay below 2 degrees Celsius. It is also more likely than not that global warming will stay below 1.6 degrees Celsius and then decline to below 1.5 degrees Celsius by the end of the century. The third question is how we will know if our efforts to stop climate change are working. If we join our hands together to stop climate change, the benefits of our efforts will be realized in many aspects of the climate system. But those benefits may not be immediately felt. The time required to detect benefits would depend on the scale and pace of emissions reductions and climate component. For example, the impact on air quality will come quickly within a few years. A sustained reduction in carbon dioxide emissions, however, will become apparent in atmospheric concentration after about 5 to 10 years. And it could take around 20 to 30 years to see stabilization of global temperature due to natural climate variability. By limiting warming, some changes in the climate system could be slowed and others could be stopped. However, some changes in the climate system are already set in motion. Sea level rise, for instance, which we already heard, is irreversible for centuries to millennia, even if we limit warming to around 1.5 degrees Celsius. The last question is what the important messages to near-term climate policy are from this report. Our assessment shows that global surface temperature will reach or exceed 1.5 degrees Celsius of warming in the next 20 years. It is also important to note that natural climate variability will modulate human-caused changes, especially at regional scales and in the near term. By 2030, global surface temperature in any individual year could exceed 1.5 degrees Celsius increase relative to 1850 to 1900, with a likelihood between 40% and 60% across the scenarios considered here. The latest UN climate report highlights the importance and urgency of near-term climate actions. I finish here. Thank you very much for your attention. Over to you, Lorianne.
Thank you, Prof. Lee, for these comments about carbon emissions and the importance of reducing them, even though they can be long-lasting effects to reverse the trends. So I would like to thank now all the panelists for their short presentations, and we will now proceed to a Q&A session. So I would like to remind all the online attendees to post any questions you might have in the chat or Q&A function in your Zoom. And while you do that, I'd like to ask a first question to all our panelists. So for a very short answer. So having listened to all these very interesting presentations, I still have, I think, a very important question that remains in my head, which is, what is the greatest unknown or uncertainty in Asia, so for Asia, in your field of studies of the IPCC report? And what are some ways to address this unknown or uncertainty? So maybe I can start with Prof. Thorne.
Sure. So, yeah, sure. So mine is observations. Clearly, we don't know far enough back with high enough fidelity what the changes are in the region, and the reason for that is principally that we need to share more of the historical observations that have been taken, and we need to rescue those that are in hard copy or image form only. We have a wealth of stuff that we have observed that we are not at the moment using, and we need to address that as a matter of urgency. Thank you.
Thank you, Prof. Thorne. Dr. Raghavan, you have any comments regarding water cycle?
Yeah. I would just like to respond on the with regard to the monsoon heavy precipitation. We know that extremes are projected to increase, both the wet and dry extremes. But on a regional scale, when we are, let us say, for the example of monsoon, one of the uncertainties in the near term is what will happen to the monsoon, what will happen to the extremes in the monsoon, droughts or floods. There is a big deal of uncertainty, especially as I mentioned, the effect of the natural forcings like volcanic eruptions. That is not well understood. So near-term prediction, our confidence is very low. That is one of the key uncertainties, especially heavy precipitation, monsoonal changes in the near term. Thank you very much.
Thank you. Maybe now I can ask Prof. Doblas Reyes. And what I'd like to also emphasize in my question is, of course, there is a lot of uncertainty, but there are a lot of things that you know already, and you know how maybe you can address some of these uncertainties, which is very important as well, maybe in the future. So, Prof, maybe Doblas Reyes, would you have a comment?
There are lots of things that we know. These are very important things, and some of them have been mentioned here. It's for instance, for Singapore, what we know about sea level rise is critical, as has been explained. But I would like to mention that there are lots of things that we don't know, and in particular, there are many things that we don't know that are very relevant to the users, and this is particularly important at the regional scale. So we shouldn't forget that modeling of climate and the Earth system is still far from being solved. There are lots of things that we still have to do. Climate modeling is, in particular in the climate change context, is a problem that is still far from being adequate for the requirements that we're receiving from society. So observations are critical because we need to understand how the system works, and without observations, there's no model that can be developed. But at the same time, models are not there yet, and we are dealing here with a huge amount of requests from many different sectors of society that are throwing questions at us that we are still not ready to answer. So stay tuned. We will keep working. There are many decades still to really provide the information that society is requesting. In the meantime, we are doing our best, as you have seen in these presentations.
Thank you. Is there something you'd like to add, Prof. Horton, about sea level rise, the greatest uncertainty, and how to address it?
Previous three panelists sort of summarized the uncertainty to do with sea level, be it lack of observations, which hampers our understanding of processes such as groundwater withdrawal and the land substance, to do with climate modeling and our uncertainty to do with ocean dynamics here in Southeast Asia, or be it some very sort of unknown questions. So one of the things that we are struggling to realize how we're going to examine this into the future is the combination of a large megathrust earthquake here in Southeast Asia that would cause substantial land level changes both during the earthquake and several decades after it. How do you incorporate that with the changes in sea level? How are we going to solve this? Well, we're going to solve it with our fantastic students. We've been very fortunate at the Earth Observatory of Singapore to have our largest intake ever of PhD students. The vast majority of them are Singaporean, so we're going to grow our homegrown institution that will understand these climate threats now and also in the several decades to come.
Thank you. Prof. Canadell? Is there something you'd like to add for your field of the report?
Yes, thank you. So in the carbon world, one thing that for which we have very big uncertainties in the Asia region is about all the anthropogenic emissions, both the emissions from all human activities. And the reason this is important is because we use these emissions, especially explicit, which we have, as I said, large uncertainties, to then estimate the natural sinks, the sinks that relate both on land, but also the way we constrain also the sinks in the oceans and the sensitivity of those sinks to climate change and climate variability. And again, the relevance is because we know how much nature is helping us to clean the atmosphere. And of course, we want to make sure that we understand. So ways we can help to reduce these uncertainties are certainly with more atmospheric in situ observations. So Asia doesn't have a lot of, kind of long-term high precision atmospheric observations. And also the new generation of column greenhouse gases and some of the new generation radar, microwave satellites looking at biomass, carbon stocks on the surface of the land can also and ultimately help us to reduce uncertainty in this topic. Thank you.
Thank you. Prof. Lee?
Yes. Same as Krishi, since also I'm living in monsoon country, I think the largest uncertainty is in estimation of near-term regional monsoon changes. But the good aspect is that we already identify key source of uncertainties, including the internal variability, the interplay between internal variability and human caused changes, and also the role of natural and anthropogenic erosions. Once we know the sources, I think we can solve the issues. Then also one of the issue is the limitation of climate modeling, especially for the precipitation, not just the mean precipitation, but the trend and variability of precipitation simulation. But the climate models have improved, and we know what is the lack of model for realistically capturing those monsoon simulations. So I think there is hope for us to improve the projection of monsoon changes. That's it. Thank you.
Thank you, Prof. Lee. I know that Prof. Wiesbeck and Prof. Ko were not authors on the IPCC AR6, but I'm sure you have very valuable comments in terms of uncertainty and unknown for the region. So maybe Prof. Wiesbeck first.
Yes, thank you very much, Lien. And I think one point I would like to raise in addition to what the colleagues have said, in particular, our region here that we're speaking with, Oceania and Asia, is one where we have a large collection of small island states. And the small island states countries, I sometimes call them large ocean states, they look at the IPCC reports and the assessments, and certainly the regions that they are concerned of are not so well covered by the footprint and the large scale of the global model. So I think there's a need, as Paco was identifying, for the regionalization, but in particular focusing on these island communities. The same can be said for many Asian countries who have extensive shelf regions, shelf seas, think of the Indonesian Sea, think of the South China Sea and alike. And it's also not clear that the global or regional pictures that we're giving in the assessments really hold true for assessment of change. That's a data challenge, as Peter has mentioned, but also in the forecasting. So I think I would say for the Asian community and the oceanic community, I would like to see more cooperation, more getting together, exchange of knowledge, exchange of data, making that available to each other and the globe, and to really acting as a region. I think that would help to fill up some of those knowledge gaps that we do know are existing in your regions. Thank you.
Thank you very much. And finally, Prof. Ko?
For me, I think I live in Singapore, and the rain that we get in Singapore, they come in, usually the ones that cause flooding and all those, they come in very intense bursts. And these are phenomena which are very small scale. And the scientific understanding of these small scale extremal events, it's actually rudimentary. The stochastic nature of it makes it hard to approach them from the conventional viewpoint of deterministic science. And I think much more progress can be made in this regard. These small-scale systems that are kind of stochastic, embedded in bigger scenarios, like now we have climate change. So how would the statistics of these extreme weather events in terms of rainfall, how would they change or not? Because the predictions so far cover more or less something like monthly average rainfall in a monsoon region in the future climate change scenario. And then the link between a monthly average to the stochastic extremal events, it's very hard to conceptually even to make a definite link. And that's where I hope really there will be some progress, and not just a common layman assumption that when the average changes for rainfall, the extreme would definitely change in the same direction. I think we need to do more to understand that part better. Thank you.
Thank you, Prof. Ko. And to mirror what Professor Horton was saying earlier, it's very nice if we can have some students, a lot of students working on all these different problems. Thank you very much. Elle, is there any question in the...
Yeah, we have a few questions and about 13 minutes left, so we'll try our very best to get through all of them. Would you like me to ask one of the... All right, so the first question is from Smitha. Thanks for the informative presentations. I'd like to know why the graph showing equal proportions of CO2 sink by ocean and land.
I guess
I guess it's for you, yes, Prof. Kazadeh.
Yeah. So that's what it is. So basically, at this point, contemporary, we're seeing that the land is taking a little more, almost 30% of all the anthropogenic emissions, and the land 20. Historically, of course, the land has seen a lot of emissions coming from the degradation and deforestation. So the ocean historically has been more important. And as we go into the future, if we continue to warm up temperatures, the land begins to slow down with the growth of the sink, while the ocean also slow down, but less. And when we go to very, very hot scenarios, we have the land that begins to decline in some rare emissions. I'm sorry, in some rare models, we do even see the land flipping from a sink to a source. Now, we don't see this thing in the ocean as we go into very hot scenarios. The ocean always continues to be a sink, and actually it is in the very low emission scenarios in which we might be doing what we call a lot of negative emissions, like we pull a lot of carbon dioxide atmosphere, which we see the ocean perhaps also going a little as a source. But in general, remember that the sinks exist there because they react to the perturbation, which is the how much carbon dioxide we accumulate into the atmosphere. So as long as we have lots of carbon dioxide into the atmosphere, we'll have sinks. And as I said, the land and the vegetation becomes a little more sensitive in the very hot scenarios. Thank you.
Thank you very much. A question from Vina. Still trying to reconcile Lamont-Doherty models saying 10 years ago, oceans were much warmer. What are the measurements taken, please?
Probably for Prof. Wiesbeck or for Prof. Thorn.
Yeah, I'll take a stab at that. I think the measurements that we have about ocean warming are based for something like over 100 years from surface measurements. That's largely from merchant ships trading the typical trade routes between Europe, Asia, North America, and Africa and alike. So that's a pretty solid data set that looks only at the surface. And then about since the 1950s or so, we have an increasing number of temperature measurements of, let's say, the upper 200 meters of the ocean, in part by automatic probes that you drop from running ships, and the scientists have been amassing that. And maybe over the last 20 years, we have a much more substantial observing system with robots in the ocean that gives us a chance to look at the warming of the ocean. But all of these records, if you look at them in detail as we do, at the global scale, there's pretty much almost a linear growth in the uptake of the heat. At the regional scale, there's certainly ups and downs, which is modulated by effects like the El Nino Southern Oscillation phenomena and other regional changes. But actually, the ocean warming goes much more steadily than the atmospheric warming. And over the last 30 years, we have high confidence in the numbers. Over the last 50 years, we have some decent estimates. But before that, it's too sketchy to know from the observation that we have.
Thank you. Prof. Thorn, would you like to add something regarding the data?
That was a great answer. I suspect the question might have been about the surface warming and the modifications to the estimates of surface warming between the 5th assessment report and the 6th assessment report. Part of that is about better handling the difference between ships and buoys. So in the 1980s, all measurements were from ships. Now, surface temperature measurements, 90% of them are from buoys. That matters because the ships and the buoys read systematically differently. The buoys read cooler than the ships do on average. And if we don't account for that, we would underestimate recent warming. But it's not the only reason that surface warming estimates have increased. There's also been fantastic efforts at accounting for data void areas over both the oceans and the land, and also the ice. And those together have meant that on an equivalent measure to the AR5 assessment, we're estimating about 0.1 degrees more of warming that occurred. That doesn't, of course, mean that more warming occurred. It means that our estimate of the warming has modified. And that's really important to stress. The real world has warmed one way, and it's our estimate of that real world warming that has changed. But that has really important implications for Paris Agreement and the possibility of meeting the temperature target of keeping well below 2 degrees and striving for 1.5. If we've really warmed by 0.1 degree more, then it's that much more challenging.
Thank you, Prof. Thornell. Is there another question?
Yes, we do. From Xiangzhong. This is for Professor Canadell. Thanks for the presentation. In addition to reducing human GHG emissions, what would you share? Would you share some perspectives on using natural carbon sinks to mitigate climate change, and what are the challenges involved?
Yeah, so this is a great question, and it's very difficult to actually put numbers to some of these, questions. But let me just give a ballpark number for people to understand where the big effort is in bringing the whole climate to stabilization. And so if we were to give some ballpark numbers, would be that we need to make a 90% of all the effort we need to make, 90% would go into reducing emissions. If you look at carbon, would be emissions from the combustion of fossil fuels. And then we have 10%, which again, it can be very different depending which kind of climate stabilization we're looking at, in which what we call the nature-based solutions can play a really important role and or must play a very important role in the case of the Paris Agreement targets, in which we have to do what we call negative emissions. That is, it's not enough to go to zero with all the carbon and as much as we can from other greenhouse gases, but also we have to remove carbon dioxide from the atmosphere in a way because we're a little late. You know, we've been, as I showed, we have increased emissions very rapidly over the last 30 years. Now, we can invent, as we are doing, machines to take carbon dioxide from the atmosphere. But in terms of the bulk, we really have huge opportunities with nature-based solutions, not just reforesting, left and right, but there's a lot of degraded ecosystems. The biosphere has been depleted over the last 300 years of a lot of the carbon stock because land clearing, land degradation. And there are wonderful opportunities to really bring this carbon back. Now, the ocean can also play a role there. It's a little more complex, we know less. There has to be a little more research, but we do have a few good ideas, both from a chemical point of view or biological, that can actually also try to increase the sequestration of carbon. We don't know all the side effects, and that's part of your question too. And some issues, that's why many governments have been very cautious about approaching certain aspects of the use of oceans and land for increasing carbon sequestration. But as a whole, I would say there's a huge role for it. It is still a relatively smaller role compared to the huge role of moving away from the combustion of fossil fuels. But we need to be careful about when we do this thing at large scales of any unintended ancillary impacts. Thanks.
Thank you. We have two more questions. One of them is from Ambun, and does the IPCC have a plan to produce the urban climate forecast in the future?
Shall I?
Okay, so
yeah. Go ahead, please.
that would go for me. Well, the IPCC is not making forecasts by itself, so it's gathering information from the research community and synthesizing it and providing messages that are that reflect the consensus in the scientific community, and that we shouldn't forget are approved by in a unanimous way by all the governments that are part of the process. However, the community is moving quickly towards facing the requests for urban climate change information. There is even the plan in the IPCC to commission special reports on urban climate in the next few months, which promises to really make the point on what are the main gaps in the knowledge. So somehow, I wouldn't say that the IPCC is going to make forecasts for urban climate, but is going to recognize the really rapidly moving sector of our community that is working on this particular challenge. Basically, because there is a huge demand for this kind of information.
Thank you very much. All right, last question. That is from Melvin. Will these new findings revise our current understanding of the ENSO and other climate weather systems across Asia, Oceania?
Prof. Ko or?
I can take that if you want. So the question is about the El Nino Southern Oscillation phenomena and how that will change in the future climate. If you look at the latest assessment, it says there's an indication that maybe some of the ENSO events are going to get stronger, but actually the science in the Workland Research Program, I know Krishnan is part of that group, where we're looking into it, and it's a hard problem because on the one hand, it's a coupled atmosphere-ocean phenomena. We can do some forecasting, so great slides there, but understanding exactly how that interacts with climate change is not so easy because it's also coupled in on the land on the long run. So I think there's an increasing understanding of how El Nino Southern Oscillation is probably changing under climate, changing under the climate change that we see under the warming. But I don't think there's a definite answer yet. We're understanding more of the complexities of it, and actually we will probably also have to say, and Krishna should come in there, that some of the models that we're using for that assessment are not agreeing all of them. But there is some interesting signs that we're learning about that, but the message is not so clear that you can easily say they're going to be doubly as big as we have them right now. That's my understanding. Krishna, you want to add to that?
Yeah. Thank you, Martin, and thank you for that very important question. I agree with what Martin said, that our understanding of ENSO is not perfect and how it is going to change in a warming climate. In the AR5, it was assessed that normally the Walker circulation in the Pacific, there is large-scale atmospheric circulation known as the Walker circulation, which is part of the ENSO cycle. It is supposed to weaken. This was the traditional understanding in a warming world, because the water vapor will increase at a very fast rate, but the precipitation in the Western Pacific may not increase at the same rate. So the east-west gradient will basically, in the tropical SST gradient in the Pacific will weaken, and the Walker circulation will weaken. But recently, some studies have actually questioned that. In fact, when you look from 1998 to, let us say, up to 2012 or 13, the Walker circulation was actually very strong. It had actually intensified despite the warming. And people say that this is, of course, related to a part of the interdecadal variability, the pole phase of the ENSO and so on, very prolonged Pacific decadal oscillation that happened. So there are uncertainties how the way internal variability will interact with human-induced climate change and what will be its consequence on the ENSO. This is still a lot of open questions, and cloud feedbacks are going to become very, very important. And these are still topics for research in the future. Thank you very much.
Thank you. And maybe just a final remark from Prof. Ko here.
Well, I want to add something about this thing about understanding ENSO and what the models do, because I think the challenge of all models is always for phenomena that are generated for some kind of intrinsic instability, something that is unstable in the dynamics, and then the model is supposed to reflect that. Models generally don't do well because there's a lot of positive enhancements within the dynamics itself. And then for the ENSO case, it's one such natural occurring phenomena that is due to an intrinsic instability in the system. Then there's an added challenge, which is observations, because ENSO happen not so frequently. So in 10 years, you may have 1 or 2 or 3. And then our consistent records of these events don't date back so long, only a few decades. And so from the observation side, we don't have enough data also to be able to constrain this model behavior. And so in a case where the model is especially sensitive to phenomena like ENSO, and then without a long record of these events, it makes it very hard within a short while, within the next 1 or 2 decades, to really improve this modeling of ENSO and have it explain the real world phenomena, and then to make confident projections in the future. This is very hard for ENSO. I think it's an inherent challenge of modeling unstable phenomena due to intrinsic instability and the lack of data, because it's such an infrequent phenomena occurring every 3 to 5 years. Yeah.
Thank you very much, Prof. Ko. So with this, I'd like to close this session, but first thank all our panelists for these very comprehensive, insightful, and sometimes worrying presentations. Thanks for addressing the questions from the audience in a very detailed way. And with this, I'd like to welcome back Elle for the final remarks. Thank you.
Thank you.
Thank you, Lauren and panelists. Oh my God, I've learned so much. I don't know about you. And I hope that the information that you got today will give you the impetus to act now so that we can have a better world. Now, don't forget, tomorrow, join us. We've got 2 amazing sessions. At 9:30 Singapore time, we're going to have a session on exploration and science. Ooh, I cannot wait. And then at about 4 p.m. Singapore time, we'll look into the future opportunities of geoscience education. So please, in the meantime, take care, be well, and from AOGS live in Singapore, goodbye.
Thank you. Bye-bye.
These are the words that we need to hear. Listen to the messages loud and clear. Professor Thorne got the facts around our human influence, uncharted territory with multiple references. Dr. Ruggevan gave us the science of climate change on our water cycles. Professor Cole helped with dynamic evidence to help with the scientific confidence. The ocean is hurting from our human pressure. Modern call to change our ways forever. Yeah. Climate change will not beat us down. It affects us all. We must answer the call. And it starts with us, and we must start now. Well, Francisco helped us understand the information and the problems caused by urbanization. IPCC poured over the literature to give us the truth the bigger picture. It's a hard time. Carbon budgets and the AR6. Professor Canadell is in the mix. Professor Lee has shown us the way to improve day by day. We know the sources, so we know the solution. It's time for action. It starts with us, and we must start now. Future students are the key to fixing our mistakes. The time is now, no higher stakes. It affects us all, we must answer the call. Climate change will not beat us down. It affects us all, we must answer the call. And it starts with us, and we must start now. These are the words that we need to hear. Yeah. Listen to the message, loud and clear. Our children's world. Oh, it's in our hands. Today is the day. Is the day. Take our stand. These are the words that we need to hear. Listen to the message, it's loud and clear. Time to listen. Our children's world is in our hands. Today is the day to take our stand.